Welcome everyone to the What's a Microcontroller with Python and the Microbit workshop. And heavens, I just noticed a typo here. Let's see, April. There we go, at 3 p.m. Pacific. Boom. All right, well, welcome everybody. Hope the rest of the workshop goes more smoothly than slide one. On to slide two. Stephanie, could you paste in a link to this slideshow so that everybody can have it?
Sure.
Thank you. And then for anybody watching on YouTube later, if you're registered for this workshop, you will receive this in your email, and it'll go also under the YouTube video in the more info section. Okay, so this is your crew today. On the left, there's me, Andy, Lindsay. I'm an applications engineer at Parallax. And then Ari Alvarez, our company vice president, and Stephanie Lindsay, our product and documentation manager, will be on the chat, and Stephanie also likes to chime in with questions that you share in the chat that seem relevant to the workshop. A little more about me. I'm an electronics engineer by training. When I started at Parallax, though, I ended up revising a textbook for my internship, and then have since continued to write textbooks and develop educational material, curricula, and also educational kits. And I also work under the hood in designing products like these to make sure that they work well for you and your students. Here is the previous workshops that here's the Cyberbot one, and it's going to look like this after all 3 sessions are done with this workshop. You'll be able to go to the same page where you went to read about the workshop and sign up. It'll be in the past workshops section. So like if you go to community, hover over, and then Parallax events, and then this workshop will end up in the past events area. And then you'll be able to go to it just like this one here. And so this is for the Cyberbot robot workshop that we did earlier this month. And here are all 3 YouTube sessions. And then the presentation slides are down at the bottom. So that's the way it'll look. But I will be emailing you the YouTube link for this session as soon as it's ready if you are attending. A little bit about Parallax. It's a small company in Rocklin, California, just outside of Sacramento, dartboard center in the state. We have about 20 employees and have been around since 1988 and doing education since 1997. The major emphasis at Parallax has been the programmable brains inside electronic devices. They oftentimes interact with circuits and other devices like motors and displays. So whenever you press a button on a device or hear it beep or see the display update or hear the microwave emitters in your microwave oven start, that is all, when you're pressing the buttons, you're interacting with a microcontroller. And so microcontrollers are inside most of the products we're familiar with and use on a daily basis, but they're also inside cool inventions. And by learning a little bit about electronics and how to program a microcontroller, you too and your students can invent these great things. Chip Gracie started Parallax back in 1988. Ken Gracie came on board later, and he's our CEO. Chip is mainly our chief inventor and continues to be at the forefront of new microcontrollers and microcontroller development. His big hit back in the mid-90s was the Basic Stamp 2, and this is what got the entire educational wave of microcontrollers plus electronics started. This is the first time that folks who wanted to do hobby or educational electronics did not have to do it at the electronics technician or engineer level, because he made a very easy to use programming language and system. Fast forward 20 years and the microbit is kind of in the place that the basic stamp used to be back in the late 90s. It is currently one of the best available resources for use in education. In addition to its microcontroller, which is right here, and then it has a second one that's dedicated to talking USB. In addition to that, it's got a built-in speaker if you have the version 2. It's got a couple of push buttons on the front, a little LED matrix display, which you got to try out earlier on, USB connector, reset push button, and then built in where you can't really see it, it's got an accelerometer, which you can use for doing things like counting steps. It also has a built-in compass, a built-in radio for talking with other microbits, a built-in light sensor, and there's probably a few more that I'm forgetting off the top of my head. I'll try to mention it if it comes to, yes. There's a small hole in the microbit 2 right about here, and that is for detecting elevated sound levels. And then this is also a touch sensor, which gives you essentially a third push button on the top. More about microbit-only educational resources can be found in this 2-hour YouTube video. There are actually 2 of them, but I think I covered most of the important stuff in the first workshop. And then here also is a link to the slideshow for that workshop. So if you're curious about getting the students ready for the material we're going to be covering during this workshop, this is a potential resource for you. All right, we're partway through the intros. Today, we're going to talk a little bit. We'll have some questions and answers about the coding assignments that went out in advance before the workshop about programming with MicroPython and the online editor. And after that, we're going to put together the kit and test it and just make sure everything works. And then for homework, I'm going to have you add some LEDs, that's light emitting diodes for lights, and some push buttons. So LEDs are digital outputs and push buttons are digital inputs. But unlike the ones on the microbit, we'll be building these and connecting them to the microbit. We'll build them outside the microbit and connect them to the microbit. Here is the exploded view of the kit you received in the mail. Its part number, and then a link to the product page at Parallax. And also a link to replenishment parts. If you order a classroom's worth of kits, I recommend getting a few extra bags of these small electrical and electronic parts because they're easy to drop, step on, lose, etc. And so these really come in handy. The microbit can do a lot on its own, as you saw earlier, with the built-in radio and compass and etc. But some applications need more. And that's where this kit comes into play, because it gives you a platform for doing actual circuit prototyping. It's also kind of a next step after learning about how to program the microbit just as a standalone device. The kit is focused on pre-engineering and STEM and is most commonly used in the CTE engineering, computer and electrical pathways. The estimate for the amount of time this class takes is 40 hours. And it can be used before, after, or in parallel with the Cyberbot robot, which I mentioned earlier and showed you where to look at the most recent previous YouTube video. Electronics and technical things have become increasingly relevant, especially with manufacturing concerns. Cyber.org is devoted to developing a cyber-ready workforce and is a contributor to this curriculum. Here is, for anybody coming back or coming in later, is not part of the workshop, did not get all the emails I sent out, but you want to watch it on YouTube. This is, there's a link to a document that covers everything that we did getting ready for this workshop. This is slightly different from the one I emailed you, but it's that I emailed everybody attending. It's a little bit more complete. And we'll be doing these cyberscope tests today. And also there is a walkthrough video that shows essentially everything in this document followed step by step. And with all that said, we are 11 minutes into the workshop, and let's not do any more. Well, actually, we're very close to getting started. I was going to say, oh, we're going to jump in, but there's just a couple more things to talk about. The first one is learn.parallax.com. This is the place to go for both student and teacher resources for any Parallax kit. And today, especially, we'll be using the What's a Microcontroller with Python and the microbit student resources right here. So each one of these tiles sends you to what's akin to a booklet or a chapter. We call them tutorials. This one, for example, should ring a bell because it's the Writing Microbit Programs chapter. And so, for example, as part of the homework, you went through and tried all the beginning scripts that talked about, that introduced basic things like communicating with your user, remembering and using values, solving math problems, making decisions, counting and repeating, and then comments for reminding yourself what you meant when you wrote that line of code at a later time. Are there any questions about this homework before we keep going? Get everybody up in my screen here. Are we doing okay on the homework? Did that mostly make sense? Okay, please chime in with questions. Stephanie will be watching the chat. If there's anything in particular you wanted to ask about regarding that homework. Otherwise, it's fairly simple, or at least it seemed to me to be fairly simple. I guess one thing I would like to say about it, though, is that when your students are doing it, it's best that they go to learn.parallax.com, just like we did on the other screen. And then What's a Microcontroller with Python? And then if we're looking at the Writing Microbit Programs tutorial, it's best to have the tutorial and the programming environment tiled side by side. That way, when you are working, or when the student is working through the tutorials, they can, I'm going to do something that I recommend that they not do, which is copy and paste, because that has a strong ability to short circuit their learning and apprehension of the subject. So in a 1.5 hour presentation, I need to do that to keep up the pace and make sure you get to see all the important stuff. But if we have a student in the classroom, we'd want them typing out from microbit import star, and then also typing all these other lines, getting their indentation right, making a mistake in the indentation and struggling with it, struggling to understand what happened. Along those lines, while we're here, if A is 89 and B is 42, Well, A is greater than B, so we would expect this to display.scroll A is greater than B. Now, how would we know that? Well, what we can do is hit the connect button. And I'm going to unplug my microbit and plug it back in so that we get the dialog that you normally see the first time you connect it. Okay, connect. I didn't quite give my computer enough time to, I should have left that screen up. That particular message comes up if you maybe go a little bit too quickly while you're getting ready to connect your microbit. And once it is ready, then you'll have a choice. You may have more than one microbit. You'll see something like BBC microbit CMIST app. You have to click that and then click connect. And then after that, you're ready to load the code by clicking the flash button. Now, in this example, you'll end up seeing the results on the microbits LED display. So there's a reset button right here you can use to restart your program. And it's going to tell you that A is greater than B. I know that may be difficult to follow, which is one of the reasons why in the very first test script I had you do, we used print instead of display.scroll. So we could say print A is greater than B. And once you do that, if you flash, the messages will not appear on your microbit. So when I reset it now, reset button, press release, notice that nothing happens on the LED display. Well, that's because we're using print, and print sends its messages to a different place than display.scroll. Print sends messages to the serial terminal, which you can get to by clicking the open serial button. Now, if you want to restart the code, you can press and release the reset button again. There it is. And you'll see the A is greater than B result. Another thing you can do is do it right from the terminal by clicking Control-D to reset. And then the result is displayed again, and again, and again, etc. Now, one last thing, if you make a coding error, if your students make some kind of coding error, like let's say the cat stepped on the keyboard, and so print is misspelled. When we run this, yes, there will be an error message displayed on the microbit display. It goes by pretty quickly. Sometimes you can read it and find out what line the error is on, but for a better view of that, you can also hit open serial, and it'll tell you exactly what line it sees the problem on and what it thinks the problem is. And then we can go and correct it, and then our program will work. Indentation is important. If you want to do two things, like maybe both print and display on the display, like so, they both have to be indented below the if condition. So when you have basically anything that ends with a colon, you want to see whatever you want to happen as a result of that thing, be it a decision or a repeating loop, you want to see that below and indented. And then the next non-indented thing is comes after it's done with all this. Saving your work. There's a load save button. Make sure to click download project hex. And it appears down here. And that in turn appears in my downloads. Microbit program 3.hex. That might be a little bit difficult to see. I apologize. Let's see here. There we go. Microbit program 3. Right at the top of the, and if you sort by date modified in descending order, I believe, then everything you save will appear up top. Now, when you can also change the name of your program, for example, test conditionals.
We have a question.
Okay, let me save my work before answering the question. So again, hit load save, download project hex, and now we have test conditionals here. Okay, what is the question?
What is the difference between download Python script and project hex?
That is an excellent question. Download Python script works most of the time, but there are some drawbacks to it. First of all, when you click download Python script, notice that there is a warning down here that you're downloading a script, which in this case, we trust the script, but your browser is going to pretty much always say, hey, this could be a problem. The second thing is that sometimes these scripts contain extra files that are needed to help the scripts run. We'll be doing a lot with that on Wednesday. Those extra files will travel with a hex file. They will not travel with just a script. You have to go through the extra steps of adding whatever extra files that contain functions and methods that then your script can utilize by going down here and clicking add file and then finding the particular module that you want to add to your code. I'm getting a little bit ahead of myself with that, so and I also somehow cannot see. I do not see the close window for that.
Does the script down? Go ahead.
You can cancel from the.
Thank you. There we go. Okay.
And another question has come up, if it's part of this too. Does the script download as a PY or hex file?
Okay. So when you click download Python script, it downloads as testconditionals.py. When you download a project hex, it downloads as testconditionals.hex. And now that I've downloaded testconditionals.hex, one thing I can do is, let's say we refresh our browser. Well, all of a sudden, all work is lost. And what comes up is the default script. In most cases, you can simply open your file browser and drag and drop a hex file or a .py file onto your browser when you're at python.microbit.org, and it will automatically open for you. And if you have a script that contains code modules with, added features, you would be able to see those down in the load save area. There would be a second file here. Whereas if you instead loaded testconditionals.py, yes, it would open, but again, it would not carry those extra files with it. So the two things about the hex file are, one, your computer doesn't warn you that you've downloaded something potentially dangerous every time you download the hex file. And then two, it carries anything that you've added file-wise along with it. So that's why I recommend always using download project hex. And you'll see quite a few examples of that coming up. So by setting a script name before hitting load save and then download project hex, that's the name that the file gets. One other thing is you can also open that file by clicking load save, then clicking or browse for file, and then browsing to.
Mark pointed out you still have a typo in the word print. Is that intentional at this point?
Yeah, I was testing how much attention everybody was paying. Thank you, Mark. Okay.
Oh,
So-
and oh no, that was Robert. Sorry.
Oh, thank you, Robert.
But Mark does have a question. Does a microbit require a hex filter to run instead of a PI file? A hex filer.
A hex file. Either way is fine. I believe the hex file is what the microbit receives. And the hex file actually contains the Python script, but it also, as I mentioned, contains additional information. I think it contains the runtime in some instances for the microbit to use, and it also contains sometimes modules that are added to it. So again, even though it's Python, and so you'd think, yeah, it ends in .py. No, it's really best to always save everything as a hex file. Okay, let's see. And then, so we talked about save as, which is essentially change the script name and then download it again. And we talked about how to open by clicking load save and then selecting or browse for file. And then they're going to appear in your downloads, but you can certainly move them wherever you want and store them in whatever neat and organized place works best for you. And so then we can use our side-by-side technique to keep on going through tutorials. And I highly recommend, again, have your students hand enter their code, give them quizzes and homeworks, which we provide a fair bit of that, and we'll go over that on Friday, pre-solved homework for you that you can share the questions, exercises, and projects with them without the solution. And that should help motivate them to, you can use that to reinforce, hey, look, when you hand enter the script, you think it through more carefully. It causes questions to come up. You naturally run experiments. And then also, you can continue through the lesson, but you'll be able to follow it better. If you copy and paste like I did, that's going to be a significant hurdle to learning the language well. All right, so that's it for the talking about stuff. So now let's start by digging into our kit. Here is the first lesson, and by the way, you would get there by going to learn.parallax.com, clicking what's a microcontroller with Python in the microbit. And in this case, we're going to go to breadboard setup. You don't need to go there because it's on the screen. I'll paste you a link if it's something that that you'll need to potentially keep looking at even after I've moved on to another slide. So the first step is going to be to connect the microbit to a breadboard. But before that, for those of you who are unfamiliar with breadboards, I'd like to talk about that for just a second. So this whole thing that's in the box we sent is referred to as a breadboard. And that came from the fact that in the old days, electrical things were prototyped on actual wooden cutting breadboards, breadboards for cutting actual bread. And there's two middle parts that are called terminal strips. And this is where we normally connect wires and part leads to each other. And the terminal strips have column letters and row numbers. And you can play a battleship with this by saying, hey, column G, row 16. Well, it's that socket right there. And there are some cases where I do call out in the tutorials, I call out, hey, put the wire or part lead in, column G, row 16. This appears as an animated GIF file on the web page, but then for the sake of lecturing or in some cases following along, we put an MP4 version that when you click it, it opens in another screen, and then you have pause control, and you can go to different parts of the video to answer questions or talk about things at length, as opposed to the animated GIF, which is just going to cycle through, and you may find yourself having to go through it a couple of times in order to get there. All right, so here is one where I will paste in the link, because these are the first parts that we're going to gather. Chat. Okay, so that's in case we run out of that's in case you need more time to look at it.
We have a question.
Yes.
Are those two separate breadboards? Are there two G16s?
Oh, yes, that's a good question. When I was going through the workshop, I wondered if somebody would be asking that. Yes. So in the documentation, I end up saying use G16 in the terminal strip on the right or in the terminal strip on the left. And yes, there are two terminal strips. There are also 3 bus strips. I think I might have stopped that video ahead of time. The bus strips are these ones with the vertical red and blue lines. And so there are 3 bus strips separated by 2 terminal strips. More about that in just a minute. What I want you to do first, though, is gather these parts. Can everybody see those okay? Okay, getting some thumbs up. What happens if I zoom in one more? It gets smaller. Okay. Bear with me just a minute. There we go. Okay, I'm going to do this along with you. Okay, this is the Edge IO adapter right here. Comes in this silver anti-static bag. And there's a piece of foam, anti-static foam, connected to the bottom. It's not to protect the device from static so much as it is to protect these pins that are sticking out the bottom from getting squished during shipping. We already have our microbit and USB cable connected. And the other item is the breadboard. So there we go. All right, was I the last one? Everybody got it? Have you got all your parts? All right, good, good. And then feel free to unmute yourself and say, hold up, Andy, I need just another half minute. Or Stephanie might catch it in the chat. All right, so now here's an example of using the MP4 again. So what we're going to do first is take the microbit and push it into the slot in the edge adapter. And you want it to go in so that you see roughly a third of the circles on the microbit still visible. Normally we talk about, hey, you also want to always disconnect any power from your microbit. So in theory, we want the students to unplug their microbit before connecting it to the edge adapter. Next up is the breadboard. And before plugging it into the breadboard, first of all, make sure you've got it oriented so that A, B, and C are on the top left and bottom left for that matter. Once you're sure you've got the breadboard oriented so that you can read all the letters and numbers comfortably, we're going to locate the row 30 because that's where the bottommost pin on the edge adapter is going to be aligned. And we don't actually want to plug it in yet. What we want to do first is just set the microbit where it looks like it needs to go. And what you'll want to do is check and make sure that that P0 pin, that there's a pin sticking out at the bottom labeled P0, make sure that's aligned with A30. And there will also be pairs of pins that plug into the bus strip here and here. And the topmost pin looks like it should be lined up in A11. And this is all on the left terminal, leftmost terminal and bus strips. Okay, so that's right side up so I can read the letters and numbers. And there we are lined up. Not inserted yet, but nicely lined up. And once you're sure you've got it lined up with all these connections just so, then, you know, we're doing this, we're magnifying it to have your students take a nice close look and make sure that they've got all those pins sticking in the right sockets on the breadboard. Once they're sure about it, then, and only then, can you take the board. Sorry, here we go. So there it is on the side view. And then we show that you want to push it so now it's time to insert it so that the pins go all the way in and they end up stopping against the little plastic headers that that the pins at the base of each pin. So here we go. Got to squeeze pretty hard. Are we good? Okay, I'm getting some thumbs up. Since I'm not seeing any shaking heads, hopefully we're doing okay. And then the next thing would be to plug the, well, actually, we're going to leave it disconnected for a minute. Okay, so the next thing that we're going to do is learn how a breadboard actually connects two wires together. And so the theory before it is, and then again, give me a shout out if you're concerned about how you've got your board connected or need more time. Okay, so we have terminal strips. And the rule for terminal strips, if you want to connect a pair of leads or wires or any combination thereof together, the rule is that you're using rows of 5 sockets. I have a picture later that will show the metal clips that live under these rows of 5 sockets. So what you have to do is you have to pick a row of 5 sockets. And then we don't need to do this, but you can connect 2 wires to the same row of 5 sockets, and they will be electrically connected. Now, if you put a wire in a different row, that will not be connected to any of the wires immediately above it. Now, that's not to say you can't add one more wire to that same row. Then you'll have 2 pairs of connected wires. And again, the above and below rows are not connected, but if it's in the same row of 5, it is connected. So different rows of 5, not connected, same row of 5, connected. Different row of 5, not connected. Now, another thing you can do is even if you're in the same row, but it's not the same row of 5, like here's a pair of wires across the valley, and these 2 are connected to each other, and those other 2 are connected to each other. But the 2 wires that we're pointing out right here are not in the same row of 5. They're in rows of 5 that are across this little valley here. And so they're not connected. However, you can, if you want, put a jumper wire to connect the 2 rows of 5 together. Then those 2 wires, even though they're in different rows of 5, because we ran a jumper wire, plugged it in to the 2 different rows of 5, now they are electrically connected. And by electrically connected, I mean that electric current, electrons can flow from this wire through this row of 5, through that wire, through that row of 5, and out this wire, assuming that there was a supply and something to run that supply through, like a light. For bus strips, so these are the bus strips here. That was what I didn't talk about earlier. So here are the bus strips, and they are vertical. For the bus strips, we're not thinking about rows anymore. We're thinking about columns next to a particular colored line. So we have a red line running vertically here, and anywhere along this vertical column, you can plug in wires and they'll be connected to each other. And this is typically used for running power to all the different circuits that you build on the terminal strips. So the bus strips are going to be your voltage source and your ground. And one thing to emphasize for the students is, hey, just because it's next to a blue line when you plug it in, if it's not the same bus strip, it's not going to be connected to a wire that's in a separate bus strip. However, just like with the terminal strips, we can use a wire to connect the two together, and then they will be connected electrically. Zoom back out. Next up, we're going to set up a little measuring tool here. So what we're going to do is, I'm going to freeze an example of this. So just watch along here for a second. What we're going to do is gather these parts, which are, and again, I'll put this up in just a second. We're going to grab 3-pin headers and alligator clips and a red and a black jumper wire out of our box of parts. And then the 3-pin headers are going to plug in on rows 30 and 28 right next to the P0 and P2 pins on our adapter. I usually like to leave one socket. I like to plug the 3-pin headers in the rightmost part. And then we use a magnifier to make sure that the students get that right. And then we'll use our alligator clips to grab the 2 jumper wires. And we'll plug them into, okay, so here's a pop quiz. So thumbs up if those 2 wires are connected, thumbs down if they're not connected. Getting some thumbs down. You guys are on fire. Excellent. Yes, since they're in different rows, they are not yet connected. All right, so now I'll zoom in on this. So these are the parts I want you to grab from your parts kit. And at this point, one thing that works out pretty nicely is you can take your microbit box and empty out everything that's in it. Off to the side, there will be a battery pack, a little brochure, a sticker, and some batteries. Don't lose the batteries, by the way. So now that we've got our little microbit box, you can take the small electrical parts and open up that bag and empty those parts into the microbit box. And let's see, here are the jumper wires. Make sure to grab red and black so that we're sticking with the convention that most meters use. So there's our red and black jumper wires, and then the 3-pin headers.
Angelina has a question. Some of the jumper wires have words on it that say alpha wire. Is that something different?
Keep going.
Nope, go ahead.
Okay, yeah, don't worry about any labeling on the jumper wires. The color also does not matter electrically. It only matters from the standpoint of visually identifying certain things. And so one of the most standard things is that black tends to get used for ground wires. the negative terminal of a battery pack if you're using it, a battery pack to power something. And then the red would go with the positive terminal of, say, the battery pack or whatever supply you're connecting to the circuit. So there we are. And then again, we're going to plug one of these 3-pin headers into row 30, right next to the P0 pin on the adapter. And then the second one next to the P2 pin. Then grab the 3-pin header by the P2 pin with one alligator clip. The bigger of a bite the alligator clip takes, the better. And then-
Andy, can you give us a blow up of the 2 headers before you plugged in the red jumper?
Yes, let's see here.
Real good blow up.
I'm on my way. Okay, that's actually not the best blow up, is it? Because okay.
Now, can you zoom in right there?
Yes.
CD.
CDE for both 3-pin headers. CDE 30 and CDE 28. Then again, go ahead and grab those guys. The upper one with the red alligator clip and the lower one with the black. And then with the other ends of the alligator clip, of each alligator clip, put the black wire on the black alligator clip, the red wire and the red alligator clip. And then let me remind myself of what. Okay, and then F16 and J17. F16 for the red and J17 for the black. And then when you're ready, go ahead and reconnect the USB.
Let's see.
Here's an observation about Chris mentioning not liking how close the 2 clips are together. Students will short them together.
Yes.
And it says, I would recommend jumping over to the right side of the board for either the red or the black or both. I'm not sure what that means, jumping over to the right side of the board.
Oh, yeah, what he's suggesting is to, first of all, it's not going to hurt anything if they're, aside from they'll get bad measurements and learn a lesson about, or incorrect measurements and learn a lesson. So he's saying something like this.
Oh, and then moving a jumper wire over to,
Yeah.
okay.
And that's at the discretion of the teacher. The documentation has it like this.
Mhm.
And again, I think that first of all, that I'll make a note for the teacher's guide.
Mhm.
We want to just add a little something about that this can either be placed elsewhere at the discretion of the teacher, or that it can be a moment where they learn about a short circuit.
And Edwin mentions moving it up to P5 on the IO board. However, that would mean that you would need to change scripts, I assume.
Yes, and the number of hours it takes to redo the animated GIFs that are supporting all that.
Yes.
Yeah, that's an expensive.
Well, I mean, not for our tutorials, just if that's the preference of the teacher, that they would need to keep track of what IO pin changes they made. Or
I think a jumper, I mean, I think the best solution for if you're really concerned about that and feel that it's important to avoid is to basically use a jumper wire to go from P2 up to, say, row 7.
an empty row. There you go.
Well, I didn't do a very good job with the wiring, but that will work.
And so that's good to know.
Yes. Yeah, that's the best place if you need to, if you're concerned about keeping them far away from each other.
Andy, are the red and black jumper cables touching all 3 pins of the headers?
Yes.
Okay.
Does it matter?
Well, it usually matters just having a good grip on as much metal as you can. That will help make sure that you have electrical continuity between what you're testing over here and the parts of the microbit that are measuring it.
Mm-hmm.
So yeah, if it's just barely hanging off of one pin, the likelihood that the measurement won't be as good is increased. And joggling the table might cause the measurement to skip a little bit. So yeah, having them all, having the alligator clip take a big bite of the 3-pin headers is best. All right. So now we're going to have you download a script. And there is a video clip of this as well, but go ahead and watch me do it on the screen instead. What you want to do to download this hex file is right-click the link and then select Save Link As. And then it'll, offer to download Continuity Tester, and you can to your downloads. And so go ahead and click yes. And Continuity Tester will also appear here on the bottom left of your Chrome browser. Okay, so now once you've downloaded Continuity Tester, what you can do is drag it and drop it from where you downloaded it onto the python.microbit.org editor. once you've got that, click connect, select your microbit, and then flash the script into the microbit. Then click the Open Serial button. Oh, that's right. Yeah, this doesn't do anything in the serial. Sorry. Close serial. Now, if you have, it's a little difficult to see here, but looking at the microbit, we're getting some video sampling rate weirdness, but basically what you should see after you run the script is a little circle with a slash through it. And that means not connected. And if you take the red wire and unplug it from the upper row and simply touch it to the same row as the black wire, you'll get a check mark. And if you have a microbit version 2, you'll also hear the speaker. And that's indicating continuity, that the 2 wires are connected. So I would like you all to try that.
Andy, one more question.
Yes.
In the event that one of our students were to put the microbit card upside down instead of the way you have it right here, would it affect the microbit card? Would it still work if it was upside down?
Let's test that. So I'm going to unplug the microbit from the adapter and plug it in upside down. Now, granted, this way we cannot see if there's continuity, but if I probe the same socket again, I don't get the beep anymore, unfortunately. So it doesn't actually hurt anything to put it in reverse, but you will not get that same beep that you get when it's in right side up.
Oh, so was the card working when it was upside down other than the beep?
Yeah, the card was still running its program. The Cyberbot actually has it set up so that you can have it function either upside down or right side up. I think for a future revision of this board, we'd want to have that also.
We have a question. Where did you copy the code from? Was that slide 69?
No, it's a download.
Oh, okay.
We're downloading this continuity tester.hex file. So we're right clicking. Oh, I'm sorry.
Thank you.
Oh, heavens. I'm sorry, you guys. I didn't paste this in. Okay, chat. Paste. Thanks for slowing me down a little bit there. So that's the page. When you get to that page, you'll need to right click continuity tester.hex and then select save link as, and then save it to your downloads. Then once it's there, you can either drag it and drop it from Chrome into your python.microbit.org editor, or you can, in python.microbit.org, hit load save, or browse for file, and then go and find the hex that you just downloaded. Huh. Okay. Save link as downloads.
Will everyone get the same noise, or will that depend on anything?
If you have a microbit V1.5, which may have come in your kit, right now, the kits are transitioning from 1.5 to 2.2. Some of the kits have 1.5, some of the kits have 2.2 microbits. The 1.5 microbits will only show you either a check mark or a circle with a slash through it. The microbit 2.0 will also, or newer, will also make the audio sound. Okay, so was everybody able to repeat that to probe two of the same?
We have an observation that with a 1.5 module, at least the check mark works with a microbit inserted right side up only.
Yes.
We have Angelina. Are you needing some assistance? You can unmute if you have a question. Not yet. Okay, we can circle back if you like. Ah, she thinks she's getting caught up.
Okay.
And then Chris lost the URL to this after learn.parallax.com. Okay, so you Chris, you wanted the URL to the code, where to get the continuity tester.hex code.
Yeah.
Or okay.
Can you hear me?
Yes.
Yes.
Okay. So I'm at where it says continuity tester.hex. Okay, I found that page. I was plugging something in when you said what to do. I'm sorry.
Oh, not at all. So now that you're there, right click continuity.tester.hex and select save link as.
Okay. And then save it where? Anywhere on my desktop, for example?
Well, downloads might be easiest, but really wherever is easiest, because you're going to, so once you've saved it, you can, like you might have it like this, where there's two tabs. Continuity tester hex will appear at the bottom of your Chrome browser. And so after you've downloaded it, you can just switch over to your microbit online editor and then drag and drop it onto the editor.
Okay, I might not have the editor open.
Okay.
Yeah. Well, yes, I do, don't I? Or is that your screen I'm looking at?
I'll paste the editor link into the chat.
Okay, thank you. And my apologies.
No, not to worry.
Uh-oh.
Yeah, no need for apologies.
I just minimized the screen. Okay, there we go. Oh, boy. That's the Python microbit org v2.
Yes.
Okay, gotcha. Thank you.
Oh, certainly.
Oops.
Go ahead and remute yourself unless you need to ask another question.
Sorry.
No problem at all.
Otherwise, I'll start whistling and
and the dog will bark and all those other things. Okay. So then the last thing is just to test and make sure that you can see the circle with the cross through it when the two wires are not connected, and the check mark, and optionally a beeping tone when the two wires are connected. Next up, we're going to add some power to the circuits. So for parts, grab 2 red wires and 2 black wires. Okay, so here are 2 red wires and 2 black wires. And this is going to be pretty simple. I'll go ahead and zoom in on how to connect those blue and those red and black wires, pardon me. So the first and most important red wire is going to go from row 11 in the same row of 5 as the 3V pin on the adapter. And it's going to go to a socket in the red column on the bus strip. The second red wire will connect the red column on the middle bus strip to the red column on the far right bus strip. Okay, so 3V to red bus strip. And then middle red bus strip to far right red bus strip. After that, we'll use 2 black jumper wires to connect all 3 blue stripe columns. So we're going to go into the socket immediately next to the blue minus sign, and then jump over to a socket by the blue minus sign in the middle bus strip. Then go from any other blue socket in that middle bus strip, and then connect it to a socket by the blue stripe on the far right bus strip. Okay. Everybody got it? All right, so I'm going to skip over a number of, there's lots of testing. We test the voltage on each one of these. What I'd like you to do is just make sure that you've got this connected exactly correct. Each wire needs to have all of its metal sinking into that socket. And we're going to have our black wire connected from a socket by the blue stripe in the left strip to a socket by the blue stripe in the center strip. Then the second black wire goes from a socket by the blue stripe in the center bus strip to a socket by the blue stripe in the right bus strip. Then the red wire is going to go from the same row as 3V on the adapter, and it needs to jump to the red bus strip. Then a second red wire jumps from the red bus strip in the center to the red bus strip to a socket by the red stripe on the bus strip on the right. So be very careful about these connections. And again, there is a very methodical, testing the voltage using our probes, but I'm going to jump to building a light. And so we'll test the voltage that way.
Before you jump, Angelina has a question.
Yes, Angelina.
Sorry, I'm not used to Zoom. So on your breadboard, it looked like you had 5 wires when you had the camera up, but that could just be me. I only have 4 wires.
Okay, let me bring the camera back up. What you saw probably are these extra wires from what we did earlier with the continuity tests that are part of the alligator clip. So
Okay.
if we forget about those, now we have 4 wires. We have the red wire connecting 3V to the center bus strip, the red wire connecting the 2 red columns on the right 2 bus strips, and then 2 black wires connecting all 4 blue bus strips together.
Was I supposed to leave in the other 2?
Well, it's okay to have them disconnected, but we're going to be taking some measurements. So you can, if you disconnected these guys, go ahead and reconnect them.
Okay, thank you.
Certainly. All right. Let's see here. Okay, so we're skipping to the LED circuit. Build the LED circuit. Actually, we want to get the parts first. Okay, so the parts we want are shown on the screen. Now there are, we don't need to worry about the brown, black, red striped part. We're looking for a red, red, brown striped part. And I will show you where to find those. Let's see here. Okay, there's going to be, these are called resistors. I'll talk a little bit more about those, and we're kind of skipping through the most important, or we're skipping to the most important parts for a hands-on experience. And I'll tell you a little bit more about how resistors work at the beginning of the second workshop. But for now, the red, red, brown striped, red, red, brown, gold striped resistor parts are connected to each other with tape. And you can just go ahead and pull one of those resistors out of the tape. And so that's your red, red, brown resistor. Then there's a light emitting diode and a black wire. So the light emitting diode will be in that same bag that we emptied into. Here's a green light emitting diode. In that same bag we emptied into the microbit box. And then the wires will go ahead and just grab a black wire. So those are the parts for our circuit. And then I'm in the wrong spot.
You have a 10-minute to the end of the session.
Sounds good. Thank you. Okay, so LED lights and sorry about this. I got a little bit lost. Oh. So this is in breadboard setup and testing. First breadboard circuit. Actually, this is a good close-up. So when you plug in your LED light, this is the right side. When you plug in your LED light, disconnect to USB first, and then put the black wire from the blue column on the far right to row 16, then put the shorter of the two pins of the LED into, no, it's not showing there, into F16. The longer pin is going to go into D16. And then the resistor will go from A16 in one end and then to the red column of the bus strip on the other end. So go ahead and build that circuit up with
16.
another way to think about it is the longer LED pin should go to the left, and the LED has to span the valley that's in the middle of the breadboard. The resistor goes from A16 to column with the red stripe. And make sure that the resistor, that each resistor lead sinks in a good 1/4 inch. If you're having trouble with one socket, sometimes you can skip to another to get it to sink in all the way. Just remember your rule about the row of 5. Now, once you've double checked your connections, reconnect your USB, and the light should come on. Like so. If I disconnect the resistor, the light goes off. But if you've got everything connected exactly as shown in that wiring diagram and schematic, the green LED will glow. And I will paste this in case anybody needs to bring it up. Okay, how are we doing? All right, way to go, everyone. So next up, I'm going to skip to, actually, yeah, I'm going to skip to electrical measurements, and we're going to actually measure the voltage at 2 spots in that LED circuit. Measure voltage. I'll paste you the, so that here's another link with a script that I want you to download and open with your python.microbit.org editor. It's on its way to you now. Okay, so when you get to the page that I just pasted you, remember, right click the program. So it's measure volts with cyberscope.hex. Select save link as, and then save it. And then go to your python.microbit.org editor and open it up. And then load the script into the microbit. Now it's going to be running, but we won't see anything quite yet. I'm going to just jump ahead a little bit here and we'll catch up, and anybody who can stay for another 5 minutes, please do. Otherwise you can catch up with it on the YouTube video. So jumping ahead, we're going to cyberscope.parallax.com. I will paste that link in to the chat. Cyberscope.parallax.com. So there it is in the chat. And what we'll want to do is, again, make sure you've loaded the script. So make sure you've flashed the script into your microbit. And then disconnect. So this disconnect, when it's not connected, it offers you to connect. So you can click connect and it shows you it's connected. If you click it again, it should show you that it's disconnected and offer you to connect. So we want, after loading the script, we want this to be disconnected. Then we'll go over to cyberscope.parallax.com and hit the connect button there. Select the BBC microbit and hit connect. And what will show you is a voltage measurement. Now, once you've got that voltage measurement going, you can use the probes that the same probes that we used to measure the continuity, and you can put it next to opposite legs in the light to measure the voltage across the light. Get my hands out of the way in a second. So now that I have them, it's probably better to, I mean, it doesn't hurt anything, but we're showing a negative voltage and that's not really the case. I meant to put the black wire to the right of the light and the red wire to the left of the light. So I'll go ahead and correct that. Black wire to the right of the light, red wire to the left of the light. And now we can see that the voltage across the light is 1.97 volts, or about 2 volts. We can also put the red wire in the same row as or basically in the red column, and we'll see that we have a total across the circuit of 3.3 volts. And we can also measure across the resistor. That's the second part in addition to the so now we're measuring the voltage across the resistor here, and it's 1.3 volts. Then measuring the voltage across the light, and that's 2 volts. So 1.3 plus 2 volts makes up our total of 3.3 volts. And that's a very important electrical concept, is that voltages in series add up to the total voltage across the circuit. It's called Kirchhoff's voltage law. And there's an entire booklet on that in the Learn site that I'll just kind of talk about in passing next session. So how are we doing with the cyberscope, everybody? Have you got that displaying voltages? I see a few thumbs up. Yeah, I'm seeing some nods and some thumbs up.
Can I ask another question? I'm sorry.
No, we really appreciate the questions. When we hear questions from you, they make their way into our tutorials. So please ask.
Okay, so mine says 1.98. I have the green light. I squealed about that.
Oh,
So-
awesome.
I have the green light and my voltage says 1.98. How do I get to the 3.3? Can you explain that again one more time?
Okay, so you are currently probing just across the light. See where my 2 probes are going in? Can you see my screen?
Yes, sorry, I muted myself so I wasn't disruptive.
No problem, thank you. All right, so right now you're measuring just the voltage across the light, which is roughly 2 volts. Now to measure the whole thing, you can take out the red wire you had on the left side of the light and connect that red wire to one of the sockets in the red center column. Like that.
Does it matter which one?
It does not, because all of these sockets in the center column that are next to the red line are interconnected. I forgot to bring up that page with that shows the metal clips inside the breadboard. Please
I
remind
think
me.
you did say it.
Yeah.
So now I'm at 3.29. I mean,
Yeah.
is that close enough?
It most certainly is.
Okay.
Yes. Yeah, this means that first of all, it means that you've got your power connected properly, which again, that's a whole activity that the students go through, and it's documented. And I skipped quite a few steps to get to here, because 4.5 hours for a 40-hour course, we kind of have to do the survey thing. And so, so here we are with basically proof that the voltage of the 2 across each part. So now I'm going across the resistor, this part right here, and we see 1.33. And then across the light is 1.97, and that adds up to 3.3. And so that's kind of a summary of another one of the activities that the students do. So, so they did a lot more voltage testing than this before getting to this point. They, for example, tested these to make sure that they're 3.3 volts, these to make sure that they're 3.3 volts. They tried connecting in the same column, and the difference should always be 0 when you're in the same column. There's lots of different things that the students do with these measurements to to get familiar with basically the electrical properties of a circuit. And we do so with the Cyberscope. Now for homework, you're actually going to be downloading the trycyberscope.hex file. And what that's going to give us is a little preview of some other measurements you can take with the Cyberscope. So I'm just going to flash this. Don't worry about keeping up with me because it's documented in the homework and there's a video that goes with it too. Okay, so
Before you move on to the next thing, I want to make sure that everyone has got caught up. We have Stacy mentioning that when she clicks connect on the Cyberscope site, it does not let her connect to the microbit.
okay, Stacy, did you disconnect from the microbit on the python.microbit.org side?
Yeah, so I flashed it and then I disconnected. And then when I go to the Cyberscope, I click connect and it lists some things, but none of them are the microbit.
Okay.
Maybe we could do some troubleshooting with screen sharing after you're done.
Yes, let's do, because I have just, yes, let's do some screen sharing and
Okay.
troubleshooting.
Yeah.
After the end of the workshop, I want to show you real quickly what's coming on the homework, because there's a little bit more than that. Okay,
She's
so
not the only one with this issue, so that's a good idea.
okay, gotcha. So we'll skip to that momentarily. For your homework, we're going to be building we're going to be building more LED lights and then a couple of push button circuits. I'm going to send you a link to this slide, which you can use to zoom in and see very clearly where to connect everything. So that's one part of the homework. And I just want to give you a heads up about these push button circuits right here. There's a slide with a close-up that shows that we want the legs of the push button coming out the side when you plug it in so that it stands across the little valley in the middle of the breadboard. Then there's a schematic just for anybody who's interested in viewing what the circuit you're building looks like in schematic form. And we accompany those with every drawn circuit diagram like this to make sure that students absorb that there are schematic symbols for all the parts and that this is another way to convey the same circuit, though it could be built many different ways than this. Then there's a short walkthrough clip of the Cyberscope. We'll have you all test out the Cyberscope and make sure that you can make all the features go. And so we'll use this Cyberscope walkthrough clip and go to 17 minutes and 56 seconds and start there. Now, this was from when I first released the Cyberscope. So I'll mention, hey, it's really important to do this because the Cyberscope is brand new. Well, it's not brand new anymore, but it's still important to try out the Cyberscope with that demo code because we'll be using the Cyberscope more on Wednesday and Friday. There's also a step-by-step at the very end of this document. And what we can do is stop recording. So this is where the Cyberscope tests are. The rest is going to look rather familiar. But then at the very tail end of this document is the Cyberscope tests function. So that goes with the video clip. And again, that'll be this slide right here. So I'll send you links to these 4 slides. And that should get you through the homework for Wednesday. And then we can go ahead and stop recording and start troubleshooting. But there is one thing I would like to talk about before we start troubleshooting, and that is teacher preferences for the timing of workshops. So previously, Stephanie, would you like to record that or should we just go ahead and stop the
I'll
recording?
go ahead and stop.
Okay, so thanks for watching and we're going to continue. We just want to talk about how the timing of the workshops work. And then we want to get anybody who's stuck on Cyberscope unstuck.